Hello, everyone, and welcome to today's live. So, with me, we have Ms Nandini Sahu, and she is a PhD student. So, she's doing research, a lot of research on how black holes, how the black hole's mass and a galaxy's mass, they both are correlated. And if there is a correlation, how does it changes in different types of galaxies, and so much more. So, I want you guys to welcome her. So, welcome, Ms Nandini. And how are you feeling right now?
Hi, am I audible?
Yes, you're audible. You're perfectly.
Yeah, I'm feeling fantastic, and thank you for hosting me on your channel. Thanks a lot.
Yes.
It's a great opportunity for me.
Yes, and I'm very excited. So, Ms. Nandini, only recently in the last week, you have finished your PhD review. So, can you tell us more about what is a PhD review and how was the last week for you?
Yeah, so the review that I had was named. It's called draft thesis review. So that is something you have a few months before you submit your thesis. So in a review that usually happens once a year for a PhD student. So you have to present a report of what you have done in past years and the projects, some of the results that you have got, or the papers you have published. So you have to present this report to your panel members. And in addition, you have to give a seminar in front of the department, presenting your work and also what are your future plans and the timelines and how when you'll be submitting your PhD thesis. Yeah.
Yes, so it's like your PhD is coming to an end. It looks like that. So, is that correct? That that your PhD is coming to an end?
I still have a few months, around 6 months, to submit my thesis. Yeah.
So it's like how has been research, in this past 5 years, and how it is different recently because of the pandemic. Do you still go to the lab, and how do you carry out any research that you have to do right now in these days?
Yeah, so pandemic has definitely delayed things a bit. And Melbourne, my university is in Melbourne, and Melbourne is still in lockdown. So the university is closed, so we are all working from home. But I am currently in Queensland, which is luckily open. So I'm right now at the University of Queensland campus.
And second, yes. So how the topic of your PhD? I know I have some idea that is rescaling between the black hole mass and a galaxy's mass. So how did you finalize that you want to do research in this particular topic, and you want to pursue a PhD in this field from this university, and even your supervisor who has done a lot of work on this field. So how did that happen?
So in my final year of masters, that was around in 2016, I was looking for opportunities for PhD, and I came across the list of projects offered by CAS, which is Center for Astrophysics and Supercomputing at Swinburne University. So I saw this project offered by Professor Alistair Graham, and the project was about how black holes about investigating how black holes co-evolve with their host galaxies, and it further linked with the gravitational waves in collaboration with OSGRAV. So, and in 2016 only, LIGO-Virgo collaboration announced the first detection of the gravitational waves from merging stellar mass black holes. So that was really a great time to be thinking about working in gravitational wave science. And because this project was something that I was I was already very fascinated about black holes, and it was something that I was ready to take up, and it will further lead to the gravitational wave science. So I chose this project, and my supervisor, Professor Alistair Graham, he is already an expert in this field of correlations between black hole mass and galaxy properties. So,
Yeah.
So I chose the expert.
Yeah, that's really student was like learning a lot about black holes and galaxies and all the large scale structures. And recently I came across this fact that every galaxy has a supermassive black hole in its center. So you must have analyzed so many galaxies in your research. Is that fact correct? And are there any exceptions to this case?
Actually, not all the galaxies, but most of the massive galaxies are expected to have a massive black hole at their center. And these supermassive black holes have masses between a billion to a million times solar masses.
Yeah, way too big.
Sorry. Yeah. And there might be some low mass galaxies which have intermediate mass black holes, which have masses between 100 solar masses to 100,000 solar masses. And so, yeah, most of the galaxies have massive black holes at their center. But like you said, there are a few exceptions. For example, there's in our neighbor, in the local group, there is a galaxy M33, which is known as Triangulum Galaxy. So it is a low mass spiral galaxy, and people have looked and they did not find a black hole at its center. So some studies have predicted a black hole mass of about 3,000 solar masses at its center. And in fact, our scaling relations also predict black hole mass about 1,000 solar mass at its center. And we think because it is such small intermediate mass black hole, its sphere of influence is very small relative to the sphere of influence of a supermassive black hole. And sphere of influence is something where gravitational potential of the black hole dominates over the gravitational potential of the galaxy. And that region needs to be resolved in order to detect the black hole. And because the sphere of influence of this smaller black hole is very small, the current resolution limit of the current telescopes, we could not resolve the sphere of influence of the black hole, and that is why probably they didn't detect the black hole mass at its center. But maybe in future, with high resolution telescopes, they might find an intermediate mass black hole. Yeah, that is it about. Apart from this galaxy, there is another massive galaxy, Abel 2261, where people, some studies have suggested that this massive galaxy does not have a black hole at its center. So it is actually a galaxy which resides at the center of a galaxy cluster. And in a galaxy cluster, there are many galaxies close to each other, which normally keeps merging with each other and keep evolving. So this particular galaxy is also a merger product, where when the black holes at the center of the galaxies came together, so due to gravitational wave recoil, those binary black holes got kicked out of the center. And that is why this massive galaxy I'm talking about does not have a central black hole. But yeah, in general, most of the galaxies are expected to have a black hole at their center. Yeah.
Yes. And it's you were talking about, like, our current telescopes have a limit. They cannot, if the galaxy is very small and if the black hole is, let's say, intermediate, then with our current technology, we might not be able to detect such kind of black holes. And that is one reason why that all the galaxies cannot have a black hole.
No, that's not the. Yeah, you're
one of
right.
the reasons, like, because we haven't detected it yet.
That's the reason why they have not been detected yet. So,
Yes,
but
yes.
they will be space telescopes. Yeah.
Yes, and also, like, with the data.
I wanted to point out the recent release. So LIGO Virgo collaboration recently, like in last month, announced their first detection of intermediate mass black hole. So this black hole has a mass of about 142 solar mass, and it is found by merging of two stellar mass black holes. So yeah, there has been detection of intermediate mass black holes, but most of the intermediate mass black holes are missing.
Yes, yes. And with our current technology, like with these kind, like this was something that was detected because of the gravitational waves. But with our telescope, can we detect this particular intermediate black hole?
So yeah, not yet. Not like people haven't tried to use the Event Horizon Telescope collaboration to look at it. So maybe if they use that collaboration, they might find a black hole, just like they imaged a black hole.
Yeah. So that is one possibility. And also, like the data that you have used, there are about 147 galaxies, and that is a very large catalog of galaxies. So in the images and in the data that you were analyzing, what which telescope have you used mainly to get the data? Like, is it Hubble, Spitzer, or ground-based telescope? So what was that telescope
Yeah.
that you used?
Yeah, so majority of the galaxy images that I used, they are from the Spitzer Space Telescope in the near infrared band. And the black hole masses, they are taken from, they are directly measured black hole masses, measured using some primary methods. And they are taken from literature where people used high resolution spectra from many telescopes worldwide. For example, the Hubble Space Telescope, Keck, and ALMA radio telescope in Chile. And in fact, GMRT has also been looking at the centers of many galaxies. Yeah.
Yeah. So that is how. So that is really interesting. I mean, with all these telescopes, and then you combine the data, and then you have the results. So mainly in the results, like you have observed the mass of the galaxy, but not the entire mass. So you just measure the bulge. If a galaxy has bulge, you will measure the mass of the bulge. So what is the difference between like measuring the mass of entire galaxy versus just measuring mass of the bulge, the glowy part in a galaxy?
Yeah. So to explain that, can I show an image?
Yeah, you can share a screen.
So let me share my screen.
Yeah.
Just a second. Um, so, so can you see my screen?
Let's just wait a few seconds. Not yet. Let's see. You can
Uh,
send me the link on my email, and then I will just share it in a second because it hasn't started yet.
uh, okay, sure.
Yeah. Uh, till then, I
So,
can. Yeah.
yeah.
Till then, one of in audience, someone has asked, like NASA has released this information that our galaxy will be colliding with Andromeda galaxy. So is that real? And someone wants to know your opinion on that information.
So actually, I saw the talk from by Lisa Harvey Smith, and he has actually written this book about collision of Andromeda with Milky Way. So yeah, that might happen because these are the three major galaxies in the local group, and it is most probable that that will happen, but that is not going to happen now. It will be, I don't know, millions or billions of years from now. So, so we are safe.
Not exactly. Yeah, we are very safe. So yeah, just give me a second, and yeah, I haven't gotten the link yet for some reason, and we cannot share the
Yeah,
screen too.
I
Yeah, we'll
think
go
there's
back to
some
this.
problem with my screen, but
Yeah, we will go back to this later after after we have covered rest of the questions, and we will come back to this one later. So like till then, you can explain about how do we measure the bulge mass and the galaxy's mass and how they both are different.
yeah. So actually, yeah, for this only I needed to show a model, but I can explain it like this. So actually we measure the all the total mass. So the thing is, we use high resolution large field of view images of our galaxies, we generate a luminosity model of our galaxy, which exactly mimics the galaxy. It captures all the photometric and the structural properties of the galaxy. For example, if the galaxy has bar or a ring, that is visible in the image. So once we have this model, galaxy model, which exactly mimics the galaxy, we identify various components of the galaxy and we disassemble the total galaxy light into its components. And bulge is one of the components of the galaxy. So bulge is this spheroidal, ellipsoidal component which directly surrounds the central black hole. The scale is much larger, and some galaxies also have a disk extending out of the bulge. And there are some spiral galaxies which have like they have bulge, disk, and spiral arms. Some galaxies may also have a bar uh, associated with the bulge. So a galaxy can be multi-component, and one of the components is bulge. So once we have this model of the galaxy, we disassemble the total galaxy light into its components, including bulge. And then we use a stellar mass to light ratio to convert bulge mass into, luminosity associated with the bulge to the bulge stellar mass, and luminosity associated with the total galaxy to the to galaxy stellar mass.
Mic. Okay, my mic was on mute. Yeah. So, and in the relations also. So when I was studying about, like, in the past few weeks, I have seen that even in your paper, is that correct? Like, some researchers, they use both of the graphs. So in graph, they will show a relationship between with the bulge mass as well as the overall galaxy mass. So and there is a relationship in that as well. Like, there are early type galaxies and late type galaxies. So both of them, when we compare, when we try to find a relationship between, either it is the spheroid mass or it is the entire galaxy mass. So the relationship we get is a bit different. So how do we explain that?
Yeah, so it is the relationship is different just because they are two different quantities. The bulge mass is just the mass of the bulge, and the galaxy mass is the mass of the total galaxy. And we actually, through our work, revealed that there's a tight that black hole mass also correlates with the total galaxy mass. So until now, people have been majorly working on establishing a correlation between black hole mass and the bulge mass. That makes sense because bulge is something that immediately surrounds uh, the central black hole.
Yeah.
And so we were thinking, and there are some galaxies which do not have bulge. There are bulgeless galaxies as well, which have central black hole at the center. So what about those galaxies? How would they fit in this black hole mass versus galaxy correlation? So so we investigated whether or not there is a correlation between black hole mass and the total galaxy mass, and we did find a correlation between black hole mass and the galaxy mass. But in addition, we found that there is not a single relation, but actually this black hole mass scaling relation depends on the morphology of the galaxy. So we found that early type galaxies, which comprise of elliptical galaxies or lenticular galaxies, which have a bulge and disk, and late type galaxies, which are spiral galaxies. So spiral galaxies have bulge, disk, and spiral arms. So these spiral galaxies fall in the category of late type galaxies, while early type galaxies have elliptical galaxies and lenticular galaxies, which have elliptical bulge and rotating disk. So we found that these early type galaxies and late type galaxies actually defined two different relations between black hole mass and the host galaxy mass.
And also, like for someone who doesn't knows how to, like about galaxy morphology, so how would you explain what is an early type galaxy, a late type galaxy, and how can we be sure that if a galaxy is, let's say, elliptical, then it has to be an early type galaxy, or if a galaxy is spherical, if we can just simply identify it as a late type galaxy that it is just recently born? How can we be sure about, just by looking at the shape and the color of the galaxy, that we can define like whether the galaxy has been recently created, or whether it was born like billions and billions of years ago? Yeah.
Yeah. So actually, in this terminology, early type galaxy and late type galaxy, this builds a lot of confusion when people hear about it. So in the Hubble's tuning fork diagram, the galaxies which were denoted at the handle, they were
Yeah.
called early type galaxies, and the galaxies which were at the thongs of the
Hmm.
tuning fork, the sorry, at the handles of the other two hands of the tuning fork, they were called late type galaxies because they were thought to be formed late. But actually, this sequence is not necessary.
Oh.
It is not actually followed. So it's not like when I'm saying early type galaxies, that means these are formed early and late type galaxies formed late. So there might be some early type galaxies, some elliptical or some lenticular galaxies which formed after a spiral galaxy. So it is just a terminology at this point. Yeah. So
Okay, okay.
now these
So it
structures.
is how they were detected that time, that early type and late type just means like in the detection of these galaxies, and it doesn't has to do anything with like whether the at what time the galaxy was created and it came into
No.
existence.
No, it
Okay,
only
I
has
had
to
that
do with
confusion.
the form of the galaxy structure, what components the galaxy has. So the like I said earlier, these early type galaxies are either elliptical, the
Yeah.
spheroidal galaxies. They are simple in
Hmm.
form, or it can be
Yeah.
lenticular, which has a elliptical bulge and a,
Hmm.
a flat disk, while late type galaxies include all type of spiral galaxies which also have spiral arms. So if somebody looks at an image and they see a spheroid kind of structure, so they'll know that it is an elliptical galaxy and it belongs to the early type galaxy category. Whereas if the galaxy has spiral arms, they'll know that it is a late type galaxy.
Yeah. And also, like when we plot a graph between early type and late type and black holes mass, so can we infer just by looking at the galaxy and the bulge, can we infer what is the mass of the central black hole? Because we can only see the galaxy, we cannot detect every black hole. We can only detect every black hole that
Yeah,
why
that is
the
right.
galaxy is shining. So how to calculate the mass?
Yeah, so yeah, you're right. And that is why we work on these black hole scaling relations, because it correlates black hole mass, which is difficult to measure, with the galaxy properties, which are relatively easier to measure. So we have established direct relations between black hole mass and the galaxy mass. So once you have mass of stellar mass of galaxy of a galaxy, you can use that correlation that we have published in our paper to predict the black hole mass,
Yeah.
or use the bulge mass to predict the black hole mass. So we have established those relations.
Okay, once we have a relation, then we can extrapolate it, and then we can find any other information. Like if we have the mass of a central black hole, we can say like the galaxy must be around this much mass, and if we have the mass of galaxy, we can say okay, the black hole in the center must be around of this much mass. Okay.
Yeah,
Yeah.
yeah,
Yeah,
that's right.
that's really good. And like after finding this relationship, so how many years it has been since we first detected that there is a relationship between black hole and a galaxy, and how do like what is the explanation that we have about this? Like, did the black hole and galaxy, were they co-evolving together, or at some point of time every galaxy just starts having a black hole, or every black hole just after few billion years it just start having stars around them? So like after the first understanding, like since that time, how we have came far, and how do we understand this concept now that they both are related, and what is the reason behind them?
Yeah, so these scaling relations, which are different for different morphology, where early type galaxies follow different relation between black hole mass and the host property, and late type galaxies follow a different relation between black hole mass and host property. Uh, they definitely suggest they are very tight. So they definitely suggest that there is a co-evolution going on between the black hole mass and the host galaxy. However, the nature of this co-evolution is dependent on the galaxy morphology. The rate with which the black hole mass grows is different relative to the rate with which the host mass grows, depending on whether the galaxy is early type or the late type.
Okay, so someone in the comments have asked, like, this is an important question, and I was also planning to ask you this. It's like, what is the scope of citizen science project, or what is the, if there are any open projects through which, some students can take part into this. So maybe citizen science and maybe something more advanced. So what do you have to say about that?
So, for instance, in my project, currently we are not offering any such project, but there is already a citizen science project related to this, the work that I do. It's called Galaxy Zoo. So it's a citizen science project where people can participate in identifying the morphology of the galaxy. So they'll be given a high resolution, large field of view image of a galaxy. They'll identify
Yeah.
the structure, the galaxy, whether it has a bulge, disk, and also a spiral arm. And based on that, they can uh, categorize the galaxy into what is the morphology of the galaxy. Yeah, and that is very useful
Yes.
to us
So yeah.
actually.
Yes. So the students who may not know what is Galaxy Zoo, so in this platform that comes under Zoo Universe, there are many citizen science projects, not just related to galaxy, but other things as well, and not just like astronomy or cosmology in general, but there are just so many different fields which can be found here. So whenever you just open Galaxy Zoo, you will see a list of available projects, and then you can choose which one they want to, like if you are interested into black holes or galaxy or pulsars, or maybe something else, that is just like finding whether it will rain today or not, or how many, how humans are growing in this country in this particular part, or how were the history books in that point of time, and if you want to recreate those history books. So there are many available projects, and citizen science means that you can contribute yourself without any cost of manpower. So that is how you can contribute to such kinds of projects very, very easily. Yes. And just a second. Okay. And then how do supermassive black holes influence the inflation of galaxies? So yeah, it is like there is one thing that is finding the correlation between both of them, and then the next thing is the co-evolution of a black hole. So BN Puneet wants to know, like, how is a black hole influencing the feedback, it can be negative feedback. So what is that about? Even I don't know much about that, like how does that work?
I couldn't hear a part of your question, but I think I get it. It is about the black hole feedback. Is it?
Yeah, it
Yeah.
is.
So yeah, so these black holes which are very active, that means when I'm talking about an active black holes, that means they are actively accreting materials from the surrounding part of the host galaxy. So at one point, when they are accreting at a very high rate, it's like they are so much full that they eject a lot of ionized material electrons in that in form of jets, which is perpendicular to the plane of the galaxy. And that jet has, of course, some molecules, gas molecules or electron, which some of which fades back, is fed back to the galaxy. So that is what referred as the black hole feedback, that black hole is feeding on the galaxy and then ejecting material when it is after being puffed up, and that ejecting material further goes back into the galaxy in the interstellar medium, and again reforms the stars, and which are further thrown back to the black hole.
Yeah.
So this is called black hole
Yeah.
feedback. However, many a lot of physics, how exactly this happens, has not been quantified, very well constrained yet. And these scaling relations, which are non-linear, the scaling relations that we established between black hole mass and the bulge mass, and the black hole mass and the galaxy mass, we found that these scaling relations are not linear, they are superlinear, suggesting that black hole is growing faster than the host
Galaxy.
galaxy stellar mass. So this it has insights for correlation between black hole mass and the star formation rate, and this information can be utilized further in studying that black hole feedback. So I'm not currently working on it, so I am not expert of that, but yeah, it somehow has some crucial information in order to better understand the black hole feedback.
Yes. And like, what would you say, like these jets of a black hole and the presence of a black hole, does like, is it helpful for the evolution of a galaxy, or it helps in just stopping the evolution of a galaxy and in a way like kills all the star formation, or it helps the star formation? Because in like in the data you have seen, like what I know is like black hole can react in both ways. In some cases, what it can do is it can like help star formation, and in other cases, it can like what is known as galaxy quenching. Like the black hole is taking all of it and is just throwing all the material outside like through these jets, and then the black hole will be growing faster and faster, and the star rate will it will be less. But in some other cases, a black hole can actually like help the stars grow, like using the material. So it will be changing the material and the outward flow in a way that it will be actually helping the star formation. So it's like, if you see any random galaxy, like what percentage you can say like, okay, this is a black hole and this is helping the galaxy, or this is a black hole, this is not helping galaxy at all and it is rather killing the galaxy?
Um, I think the way galaxies grow, so
Yeah.
in the initial times, they have a lot of gas, dust, and those come together, collapse to form bulges. So these dust particles, they collapse to form stars. So when the galaxy is forming a star, that is like the adulthood of the galaxy. And further, slowly, when the gas is all consumed in formation of stars, and then further stars are slowly fed up in the black hole. So overall, the thing is, in the later stage of the
Galaxy.
galaxy loses all of its most of its gas. So that is the way of the evolution. And about this question, whether black hole helps in this process. So yeah, so during the this process where it ejects a lot of material in the those bipolar jets, it definitely the galaxy definitely loses a lot of gas, and not a very small fraction of it only comes back to the
Yeah.
galaxy. So in a way, yeah, galaxy does lose gas, and gas is something that keeps it going. I mean, because of the gas, galaxy keeps forming the stars, and gas is something that also boosts the black hole mass greater than the host galaxy stellar mass.
Yeah. And
Uh,
yeah, that yes, yes, that helps me
so,
a bit. Like, it can be correlated with the age of galaxy as well. Like, what is the role of black hole when the galaxy is young, when the galaxy is about to die, or when it's in the middle of its age. So a black hole will be influencing a lot of things. that time. So Abhijit Chaudhary wants to know that what propels these jets, because there is a common understanding that nothing should be escaping out of a black hole. So how are these, like, they appear to be coming out of the black hole? So if somebody doesn't has an understanding, like, how can you explain that? Like, how are the jets coming out of the black hole if nothing should escape them and not even light?
So one thing is that these materials are not coming out of the black hole. It is coming out from the that active galactic region around the black hole, the accretion disk of the black hole. And but how exactly it works, I'm afraid I don't have much details of that. But yeah, these materials, they do not come out of the black hole. It comes from the accretion disk.
Even though it looks like if you are in the picture of galaxy and the 3D representation that many artists give, it looks like that is the galaxy and that is the bulge and this is where the black hole is and this is how the jets are coming. So in pictures it looks like that. So like once upon a time, even I had because scientists, they just say like, yeah, it looks like they're coming and they know the thing, but someone who is hearing for the first time, they have this confusion, like, how is it coming out? It shouldn't come out. And also I want to yes, just a second, I wanted to share this screen right here. Okay, so this is so in the research paper you have published such kind of graphs. So one of the questions that I had is some papers were using the different masses. So one of the parameters was, let's say, the stellar velocity, the other parameters were the mass of the galaxy, and then sometimes there was use of log and sometimes there was not even a use of log. So all of the graphs have one thing common, that is the mass of supermassive black hole. But the other things, what do you put down on the other axis, changes a lot, but still the kind in these quantities. So like when we use different parameters, so what do they tell about, like, do they reveal any hidden secrets that weren't visible to us in the previous parameters of the graph?
Yeah, so I lost a part of your question, but I think I got an idea of what you're asking. Sorry about that. So the thing is, we are after a correlation which might be the most fundamental, the most tight correlation between black hole mass and various galaxy properties. So that is why we investigate correlation between black hole mass and various properties. For example, the bulge mass, galaxy mass. We also use the central stellar velocity dispersion. And when I'm saying velocity dispersion, it's not the rotational velocity at the accretion disk of the black hole. It is the random velocity of stars, the average random velocity of stars at the center of bulge, which keeps the bulge from collapsing. And apart from that, we also use the central light concentration of bulges, the effective size of bulges. So when we are correlating, when we are investigating, so the correlation between black hole mass and various properties, we are actually after the correlation which might be the most fundamental, the most tightest relation.
Back again. So yes, we heard a lot about about your graphs and other things too. So you have recently published a paper too about you have recently published 2 papers, and then there was a poster also. So when I went through the poster, there were some conclusions, like after you have all these relation with a galaxy's mass and with a supermassive black hole. So they suggest that there is sometimes non-linear log relation. So what do we conclude from this? So one conclusion is obviously that they must be co-evolving together depending on the morphology of the galaxy. But what else we can infer from this data and this research?
Yeah. First thing I want to clarify is that we usually plot the data, the black hole mass and let's say the galaxy mass on the log-log scale. And when we find a linear relation on a log-log scale, It's not
Yeah.
actually linear. It is, we call it log linear. So it's just the term. So in all my plots, I have used log scales to represent the quantities. And when there is
Okay. Okay.
the slope of this relation on the log, log of black hole mass and the log of the galaxy mass, when the slope of this relation is 1, I call it linear. It is actually log linear. And in our cases, we found that all these relations between black hole mass and the galaxy mass for early type galaxies and late type galaxies, both are non-linear, that is non-log linear. So they are actually, for early type galaxies, it is has a slope of about 1.6. That means the relation is like black hole mass is directly proportional to galaxy mass to the power 1.6. And for late type galaxies, that slope is actually double of that. It is around 3. And the second part of, yeah. So these scaling relations can, of course, be used to estimate black hole masses in other galaxies. That's the most straightforward use. But apart from this, there are heaps of applications. For instance, these are used to calibrate a virial factor in a secondary black hole mass measurement methods that is used for measuring black hole masses at the center of distant galaxies which host agents. This process is called reverberation mapping. And apart from that, these black hole mass scaling relations can be used to obtain the black hole mass function of the universe, which further goes into the calculation of black hole binary supermassive black hole merger rates. And that takes part in predicting the detection of long wavelength gravitational waves by pulsar timing arrays, which are not detected yet. And that is why in next 30 years, the launch of LISA, laser interferometer space antenna, has been announced. So that will be mainly looking for the long wavelength gravitational waves. And these scaling relations will help constrain various parameters to be detected by pulsar timing arrays and the space interferometers.
Okay. Also, like I have heard about this thing that we can use pulsars to detect gravitational waves, and I have some idea about that. Like the way the pulsar is, pulsating, the pulse will change if I forgot the word. If a gravitational wave passes through it, it should have an effect on the pulse of the pulsar. But
Yeah.
how can we actually detect it? Like, because this is another way of detecting a gravitational wave. We are not directly detecting the collision, but we are just seeing that, okay, if the pulse of this pulsar is changing, then there must be a collision, or like a gravitational wave must be produced in this particular like place in the universe. So that process seems like very like long and kind of complex. So can you simplify that for me?
So yeah, the gravitational waves are generated by these accelerating massive objects like black holes or merging supermassive black holes. They
Yeah.
emit gravitational waves, and when these gravitational waves are basically ripples in space-time, and these gravitational waves can modulate. They basically delay the arrival time of the pulsars emitted by millisecond pulsars, and that delay in the arrival time, because the pulsar timing team keeps tracking the pulses of all their millisecond pulsars, they can easily detect the delay that has been caused by the gravitational waves. And so they already have the data for that, and they can detect this delay caused by gravitational waves in their data. Now, there is a correlation by Hellings and Down, 1983, where they basically present a relation about how is exactly this gravitational wave background might affect the arrival time of pulses. And using that relation, they try to constrain basically pick out the gravitational wave signal from their data. However, the sensitivity of current pulsar timing arrays is not sufficient enough to detect the long wavelength gravitational waves, the gravitational waves generated by the massive supermassive black holes. However, the smaller wavelength, high frequency gravitational waves are being frequently detected by LIGO-Virgo collaboration.
Yes, and I really hope, like, the gravitational waves astronomy is like in such a hype. Like in just the past few, like 5 years, there have been so many discoveries, and like even in India, it has just started. And then there are times when Lisa will be launched into space, and we will have more and more discoveries that it will open a part of astronomy that was never visible to us before, because we are detecting so many gravitational waves, and that is like just a leap in astronomy. We had optical, we had radio, and now we will be seeing gravitational waves. So more and more objects in the night sky. So it's like one more question that I wanted to ask you is, let's suppose like you have a very good understanding of why a black hole, and like in the galaxies that you have seen, that how a black hole and the galaxy mass, how they are both related, and this is something it should follow. So it can be a little bit up and down depending on whether the galaxy was early type and late type and the size. But let's suppose in the plotting there is a new type of galaxy that has been detected just recently. A new, we discovered a new galaxy, and the galaxy is very off the charts. Like it is not, you cannot just put it even in the grayscale. So how will you how will you like to think about like what could be the explanation that the mass of the galaxy and the mass of the black hole, they are not at all related? Let's say the galaxy is very small, and the the black hole that is there, that is an ultra massive black hole, not even a supermassive black hole, and that is the galaxy that has been recently added to the catalog. So how would you like to think, after studying all this, like what can be the possible effects that this galaxy is not following the relationship?
Uh, so just a single galaxy, I don't think we'll believe the data. Like
Yeah.
if we include that single galaxy in our investigation and we'll try to fit a line, it will change the slope of the relation. But because it is just one galaxy, will not believe it. But if we have a bigger sample, and at the, let's say, at high mass, and let's say it follows a different relation, even shallower relation than that of early type galaxies, so it is possible. However, since I have been involved in estimating black hole masses in some massive galaxies, and we have predicted ultramassive black holes as well using our scaling relations. And we have done this prediction using other methods, using fundamental plane. And those predictions are consistent with what we got from other methods. So I will say that at the ultramassive end, our scaling relations are still valid.
Yes.
It's
So it's
low
like
mass that might be a bit unsure. Yeah.
okay. So it's like it doesn't matter how much massive the black hole gets. You like the science is really working on that end. But when it comes to low mass galaxies, like maybe it is harder to estimate the mass, and there can be other reasons, hiding why they are not following. And maybe if we have a more better understanding. So yeah, that's really good. I mean, I thought if some one particular galaxy is not following, there can be something. But yeah, we there can be so many things that can be go wrong, and we cannot just change the whole law because of a single galaxy. So that is good. And also, like, yeah, I think, yeah, no more questions for now. So about your in the beginning also, I had asked how you had selected your like the place you want to study. So like if the other students who are interested, let's say who are very in high school, like people ask me that, but I think you can answer that better. Like the students who are in high school, when they like either they see these discoveries being or they see the popular TV series or somewhere in the news, when they hear about these things, they're like, yeah, that is something that resonates with me, and I want to study astrophysics or cosmology or something related. But there are not very like there's not a very simple path like how you can go through that, compared to how you can find it for the other professions. So like would you tell us more about your journey after the high school, and what advice do you have, like after being on this journey of studying astro and physics, like what advice do you have for who are like younger students who also are fascinated with these kind of things?
Yeah, they should keep their passion alive, and
Yeah.
after high school they should of course opt science in the in +2, and
Yeah.
further they should perhaps go for bachelor of science, then master of science. So although I took a different path, I chose I did my BTech from IIT BHU and my masters as well from the same place. So even if you could not do like a Bachelor of Sciences, you can still do Bachelor of Technologies and masters, and
Yeah.
in a university that does provide some faculties of related to astrophysics. So yeah, you should go through BSc, MSc in and specialize in astronomy. Take some courses in astronomy, and further you can apply for PhD if you're interested.
Yeah, so it doesn't really matter whether they are studying like BSc or BTech, because some students are like, okay, we never did physics, so how we will get into that. So even they are from the engineering background, they can find a way if they have, let's say, the related projects to it, and then it depends on the PhD, like where you want to pursue the higher studies, if they are if they are accepting engineers or not. So there are a lot of possibilities to that as well.
So it's not, I think, about the degree. If you have done any projects, for example, my course was engineering physics. So we were like on the verge of physics and engineering. We still had some courses in physics, but not in astrophysics. But I did some bachelor's project and master's project in astrophysics, and because of my interest in it, and further, I opted for higher studies in astrophysics.
Yeah, that's really good to know. I mean, because sometimes students are very confused, like what to choose and what to not choose. It's like they have so much enthusiasm and passion, but the way they see, okay, they're not finding much information on the Google or among their peers, or from the teachers, they do get a little demotivated. So your answer, I think that will be helpful to whosoever is watching, and if they are young, and if they want to pursue this path. So it's like, what are your future plans after this? Like, do you want to continue studying this, like if you have some plans regarding what you want to do, like in on researching on this particular topic or something else?
Yeah, I definitely want to continue in academia, and I'll probably want to join in the exciting field of gravitational waves. Yeah, that is my immediate plan. So after my PhD, I will look for a postdoc position somewhere where I can continue doing pursuing the long wavelength gravitational waves science.
Yeah, that is really exciting though. And also, okay, it is almost 1 hour now, and yeah, just one more question, like regarding the confusion that we have, like because of the pandemic there has been a lot of confusion, and maybe some people who had some plans, and now they have been changed. Let's say they are not going to the labs, they are not going to the places where they could do more hands-on kind of work, and even that has been affected you as well. So like I would like to end this like live stream, like when you answer these kind of questions, like in even in this state, like some people are very depressed, but on the other hand, there are missions being launched in the space, there are new kind of discoveries, especially in astronomy, like there are new kind of black holes detected, then there's life on Venus, there is like exoplanet bigger, so there are so many exciting things happening in astronomy. So it's like because you see both of the things, so how do you see these things? Like there is so much positivity and new discoveries, and on the other hand, maybe like you are not able to contribute in those discoveries because you are being limited by the pandemic.
Um, So, so this time is actually confusing for everybody, not for
Yeah.
just for some people, and
Yeah.
somehow this has affected everybody. So there might be few days where everybody feel depressed or a bit less productive about their work, while other times they gather all their passion and start working. So it's just that I want you to know that it's not just you, it happens with everybody. So maybe focus less on what you not have, like you cannot go out or things like that. You can focus on something that you wanted to learn, or you know some skills you can add in your resume, or learn something or read a book. I think, yeah, that's it.
Yeah. Like finding time for the little hobbies and interests that we were not able to find time earlier. So rather than focusing on, okay, I'm not able to do that thing, we can focus on, okay, now I can focus on this particular thing that I used to really like.
Yeah.
Okay, so that was a really good answer. I hope everybody feels a little bit more optimistic and you can find, passion and, more, let's say, inspiration for the little hobbies and interests you have. And also do let me know how did you find this talk with Ms. Nandini. And I really had, like, I learned a lot of things. That's why, I was like, okay, I want to ask so many questions, but, why just ask alone? I will bring you on here and even other people can get a chance to ask a question. So I really had a very great time. And thank you so much for, coming and sharing your knowledge and experience here.
Yeah. Thanks a lot for inviting me. It was great discussing all these things with you.
Thank you so much. So I'll just turn it off in a second. Okay, well, bye bye everyone. Have a nice day.